This is the Pentax Optio W20, released in September of 2006, and by today's standards, it just looks like an old point-and-shoot camera with a 7-megapixel sensor, a 3 times optical zoom, and a 2.5-inch screen. But there's one word printed on the front that made this camera stand out: waterproof. Pentax said the W20 could be used underwater for up to 30 minutes at a depth of 1.5 meters, or about 5 feet. And that's without a separate underwater housing or protective case. So while I tear down this camera to see what's inside, I want to go back to the beginning of underwater photography and talk about two people who helped make a camera like this possible: William Thompson and Louis Boutan. The first known successful underwater photograph is generally credited to William Thompson. He made it in 1856. William was a solicitor, which is a type of lawyer in England, in the coastal town of Weymouth. He was also a natural historian with a strong interest in marine life. He owned boats, collected underwater specimens, and used photography as part of his work. According to a later account of his life, the idea for underwater photography started with a practical question. Could a camera be used to inspect below the waterline, such as damage to the supports of a bridge, without having to send a diver down first? Now keep in mind that photography was more difficult in the 1850s. Thompson used the wet collodion process, where a glass plate was coated with a light-sensitive solution, treated in a silver nitrate bath, loaded into the camera, exposed, and then developed before the chemicals dried, all of which had to happen within a fairly short amount of time. Taking the process out onto the water meant bringing the camera, the prepared glass plate, and some kind of temporary darkroom close enough to the shore to make the whole thing work. And then there was the obvious problem. Cameras and seawater don't mix. Thompson had a carpenter build a wooden box large enough to hold the camera. The front had a piece of plate glass so the lens could see through. A heavy shutter was mounted on the outside with a long cord so Thompson could open it from the surface. Inside was a 5x4-inch plate camera, and the whole enclosure sat on an iron tripod so it could stand upright on the seabed. Thompson and his friend Kenyon rowed out into Weymouth Bay and lowered the entire setup into about 18 feet of water. Once Thompson thought the tripod was standing upright, he pulled the cord and opened the shutter. For the first attempt, he left the exposure open for 5 minutes. Then he pulled the camera back to the surface, returned to the darkroom, and developed the plate. There was nothing on it, so he prepared another plate and tried again. This time he doubled the exposure to 10 minutes. But the light was already getting worse, and while the camera sat on the bottom, water started leaking through the joints of the wooden box. By the time they pulled it back up, Thompson had every reason to expect another failure. But after he washed and developed the plate, there was an image. It was faint and hard to make out, but you could see the outlines of rocks and seaweed. It wasn't a beautiful picture, or even a very clear one, but it proved that a photographic image could be made below the surface of the sea. As the outer shell comes off this Pentax, you can see that the basic waterproofing problem never really changed. The electronics inside are not designed to work while flooded. The goal is still to keep the water away from the camera. Thompson solved that by putting his camera inside a separate wooden box. With the W20, the waterproof box became the camera body itself. Pentax covered the front of the lens with fixed glass, and the battery and memory card compartment used a locking door with waterproof packing, but the buttons still had to move, the microphone and speakers still had to work, and the camera still needed controls and openings. So every one of those areas had to be designed to keep the water outside. Once the shell is removed, the inside actually looks a lot like a normal compact camera. Circuit boards, ribbon cables, a screen, a flash, and the lens assembly. That doesn't mean the waterproofing was easy. It means most of the difficult work was built into the body around those parts. This main circuit board shows how much photography has changed since Thompson's experiment. Thompson had to prepare a glass plate, make the exposure, recover the camera, and develop the plate before he even knew if he captured anything. The Pentax could take information from an electronic sensor, process it on boards like this one, save the image to a memory card, and show the result almost immediately. But Thompson still had one major limitation. The camera went underwater, but the photographer stayed on the surface. So the next step was finding a way to bring the photographer, the camera, and the act of taking the picture underwater together. That brings us to Louis Boutan, a French biologist and zoologist. Boutan worked at the Arago laboratory in Bagnols-sur-Mer on the Mediterranean coast of France. He studied marine animals, including mollusks called keyhole limpets. And to see them where they actually lived, he learned to dive using the heavy surface-supplied equipment of the time. But that created a frustrating problem. Boutan could go underwater and see these animals in their natural environment, but he had no practical way to bring those views back to the surface. He later asked a simple question. If you could photograph a landscape in the open air, why couldn't you photograph one at the bottom of the sea? By the early 1890s, he had started building equipment to find out. And he was not starting from nothing. Thompson had already shown that a camera could work inside a waterproof enclosure. But Boutan wanted something more useful. He wanted to operate the camera while he was underwater, and he wanted pictures that scientists could actually study, not just proof that an image was possible. To make that happen, he had to solve several problems at once: pressure, camera controls, focus, movement, low contrast, and light. Boutan built his first underwater setup around a multi-plate camera, sometimes called a detective camera. His younger brother, Auguste, who was an engineer, helped place the camera inside a watertight metal housing. The housing had glass windows for the lens and viewfinder, and sealed mechanical controls let Boutan operate the shutter and change plates from the outside. A rubber balloon connected to the housing helped balance the increasing water pressure as the camera went deeper. That is obviously much larger and more complicated than the little board in my hand, but the basic purpose is related. This board contains the W20's power control and shutter switches, and the shutter button works in two stages. A half press lets the camera focus and set the exposure. A full press takes the picture. Boutan had to operate a camera through a pressure-resistant housing while wearing a bulky diving suit. By 2006, a lot of that work had been reduced to tiny switches and automatic electronics. But getting the controls to work didn't mean the pictures looked good. Boutan's early photographs were dull and low in contrast, and the underwater scenes seemed to turn gray. Water scatters light, and material floating in the water scatters it even more. The photographic plates of the time were also much less sensitive than a modern electronic sensor. So Boutan kept changing the system. He experimented with the optics, tried using a white screen underwater to reflect more light, and at one point even tested photographic plates in direct contact with seawater. Some of the results were disappointing enough that he started to wonder if the underwater world was simply too difficult to photograph well. But he kept working on it. Keeping the camera dry was only the first problem. He also needed enough light to make a useful picture. Close to the surface, sunlight can be enough. But as light moves through water, some of it is absorbed, and some of it is scattered. Contrast drops, less light reaches deeper water, and different colors disappear at different rates. Even modern underwater photographers often bring their own lights because a flash can bring back brightness, contrast, and color. Boutan had an even harder time because his photographic plates needed long exposures. So he experimented with artificial light, including a magnesium-based system that burned inside an oxygen-filled enclosure, and later electric arc lighting. But these systems were large, expensive, complicated, and required a lot of equipment outside the camera itself. Inside this Pentax, a large part of the energy needed for the flash is stored in this one black cylinder. This is a high-voltage flash capacitor. The small camera battery charges it over time. Then, when the picture is taken, the capacitor releases that stored energy very quickly to create a short, bright flash. It's also one of the parts I have to be careful with during a teardown, because a flash capacitor can still hold a significant charge after the battery has been removed. Boutan's lighting experiments required separate underwater equipment and a lot of preparation. But in this camera, the energy storage for the flash fits beside the lens and circuit boards. This screen represents another problem Thompson and Boutan could not solve at the time. They had no immediate way to check the picture. After Thompson made an exposure, he had to pull the entire setup back to the surface and develop the plate before finding out that the first attempt had failed. Boutan dealt with the same uncertainty. He could spend a long time setting everything up, make a difficult dive and exposure, recover the equipment, and still end up with a plate he couldn't use. The W20 could show the result right away on this 2.5-inch LCD. The screen had only about 115,000 pixels, which is extremely low compared with a modern phone, but it was enough to check the framing, see whether the picture looked sharp, and decide whether to take another one while the camera was still in use. Being able to see the result immediately has changed the whole process of taking pictures. Boutan didn't build one camera and decide the problem was solved. He kept changing the design and trying different approaches. He changed the housings, improved the optics, experimented with pressure, and looked for better ways to light the scene. But he wasn't just trying to make a recognizable underwater picture. He wanted photography to become a scientific tool and a way to show the underwater world to people on the surface. That mattered because scientists often learned about the ocean by pulling animals up in nets or dredges. But once you remove an animal from its environment, you lose part of the story. You no longer see where it lived, what was around it, or how it behaved there. A photograph could preserve at least some of that context. And Boutan believed underwater photography could replace some of the guesswork with something people could actually see. That goal was much bigger than just taking an unusual picture underwater. And this is where the Pentax finally turns light into an image. The W20 uses a 0.4-inch interline transfer CCD with 7 million effective pixels. And in terms of its job, this is the descendant of the glass plates used by Thompson and Boutan. This is the light-sensitive surface where the picture is recorded. But instead of changing chemicals in a wet coating on a piece of glass, the CCD turns light into electrical information. And the camera can process that information, save it, copy it, and show it on a screen without using a darkroom. The small colored piece in front of the sensor is likely part of the optical filter stack, including an infrared cut filter. Digital sensors can respond to wavelengths we don't normally want in a visible light picture, so these filters help control the light before it reaches the sensor. The springs around the sensor are more likely used for precise alignment and preload than for image stabilization. The sensor must sit at the correct distance and angle behind the lens, and even a very small error can affect focus across the picture. Thompson used a glass plate that measured 5 by 4 inches, and this sensor is tiny in comparison, but it could record millions of picture elements and produce an image almost immediately. And that change didn't come from one invention. It took more than a century of progress in chemistry, optics, electronics, manufacturing, and miniaturization. As Boutan improved the equipment, the photographs improved too. He moved beyond the early gray, low-contrast results and started building systems that could produce clearer images using artificial light. In 1899, he tested submerged electric lighting. He also developed remotely operated equipment for deeper water, using electrical controls instead of requiring a photographer to stand beside the camera. One of the best-known surviving images from his work shows a diver underwater holding a sign that says, in French, photographie sous-marine, which translates to underwater photography. The picture almost feels like an announcement. The photographer, the camera, the subject, and the sign, all below the surface. By that point, the question was no longer whether a photographic plate could capture anything underwater. Boutan had helped turn underwater photography into something that could be repeated, improved, studied, and used. In 1900, he published a book about his work called La photographie sous-marine et les progrès de la photographie, or Underwater Photography and the Progress of Photography. And that same year, his underwater photographs were projected at the Paris Exposition. People who had never been underwater could now see images from below the surface. This tiny glass tube is the other half of the Pentax's flash system. The capacitor we saw earlier stores the energy, and when the flash fires, that energy passes through the xenon gas inside this tube, creating a very short, very bright pulse of light. Boutan had to treat underwater lighting as a separate engineering project. He experimented with magnesium, and later, electric lamps. But in the W20, the energy storage, the light source, the control electronics, and the camera all fit inside one pocket-sized device. Of course, the W20 could not do everything Boutan's equipment could do. Its waterproof rating was only 1.5 meters. So it was made for shallow water, swimming pools, beaches, rain, and casual underwater pictures, not deep scientific exploration. But that limitation was also part of what made the camera accessible. This was not equipment made for a research vessel. It was made for regular people. The W20 was not Pentax's first waterproof digital camera. It came after earlier models in the Optio W line. Pentax identifies the Optio WP, released in 2005, as the first waterproof compact digital camera that could take pictures underwater without a separate housing. The W20 arrived in September of 2006, and it improved on that idea with a 7-megapixel sensor and sensitivity settings up to ISO 1600. By then, a lot of the difficult work had become invisible to the person using the camera. It could focus on its own, calculate the exposure, use dedicated underwater photo and movie modes, save pictures to an SD memory card, show them on the rear screen, and even record sound. The person using it didn't need to understand how the sensor worked, how the flash charged, how the lens moved, or how the image was processed. And I think that is one of the most interesting things about technology. The engineering can become more complicated, while the experience becomes easier. Now we are getting into what may be the most mechanically complicated part of this camera, the lens. This small motor and threaded shaft turn rotation into very precise forward and back movement, and it is part of the lens drive system, likely moving one of the focus or zoom groups. According to the official specifications, the W20 has a 3x optical zoom lens, with 11 elements arranged in 9 groups, including 3 aspherical elements. Its focal range is roughly equivalent to 38 to 114 millimeters on a 35 millimeter camera. From the outside, all we could see was a small window behind protective glass, and the lens never had to extend out of the front of the camera, but inside, several optical elements still had to move into very precise positions for focusing and zooming, and all of that movement had to stay inside the sealed camera body. This is the point where the finished camera starts to look almost too simple. From the outside, the W20 has a lens opening, a flash, a screen, and a few buttons. But inside the lens module are several glass elements: guides, gears, tiny motors, flexible circuits, and a very small shutter and aperture mechanism. The aperture controls how much light passes through the lens, and the shutter controls how long the sensor receives that light. The sensor records the picture, the processor turns the sensor data into a file, the flash adds light when it is needed, and the outer body has to keep water away from all of it. There's no single part that turns this into an underwater camera. It works because all of these parts were designed to work together inside one small sealed body. Now that the camera is almost completely apart, it is easier to connect what we are seeing back to William Thompson and Louis Boutan. Thompson needed a separate wooden box with a glass front just to keep seawater away from his plate camera. The box leaked. The first exposure failed, and the exposure that finally worked took 10 minutes. Boutan wanted to take the photographer underwater with the camera, so he had to build pressure-resistant housings, mechanical controls, optical solutions, and artificial lighting. He worked through low contrast, long exposures, uncertain results, and equipment that was large and difficult to use. But the Pentax didn't solve all of those problems with one amazing component. Instead, the camera body itself became the waterproof housing. The locking battery door and its seal protected the openings the owner still needed to use, and fixed glass protected the front of the lens. The glass photographic plate became a tiny electronic CCD. The separate lighting systems became a built-in xenon flash, powered by a capacitor small enough to fit inside the camera. Large mechanical controls through an underwater housing became tiny switches, autofocus, and automatic exposure, and the long wait to develop a plate became a picture that appeared on the screen almost immediately. Someone who bought this camera new almost certainly never thought about William Thompson or Louis Boutan. They didn't need to understand wet plates, underwater housings, pressure compensation, electric arc lights, CCDs, or image processing. They could take the W20 to the beach, use it around a pool, carry it in the rain, or put it into shallow water and take a picture. A waterproof camera like this is so common that we don't even need to think about all of the work that came before it. And now the W20 camera itself has mostly been forgotten too. It is outdated, has only a 7 megapixel sensor, the screen is small, and a modern phone can make much better pictures in most situations. But taking it apart offers a new appreciation for the work involved. This little camera is full of solutions to problems that generations of photographers, scientists, chemists, engineers, and manufacturers had to work through. William Thompson helped prove that a photograph could be made underwater at all. Louis Boutan helped bring the photographer underwater with the camera, and he pushed the process towards something useful, repeatable, and scientific. Then cameras like the Pentax Optio W20 turned those once difficult ideas into something a regular person could carry in their pocket. Today, this may just look like an old point-and-shoot camera that nobody thinks about anymore, but after seeing everything inside it and learning what had to happen before a camera like this could exist, it's hard not to appreciate this little camera. I hope you enjoyed this video, and if you did, please hit that like button. Thanks for watching, and I'll see you next time.